Hey students, we're going to start our thermochemistry unit. For this first part of this unit, we're going to be talking about heat. So first off, I want to clear up some misconceptions. When you look at these two pictures, which one has more heat? The cup of hot coffee or the glass of really cold water? Well, you can't tell just by looking at it because heat is not temperature. And a lot of students get that conception or get that idea confused. They think heat's the same thing as temperature. And temperature has, something to do with it because there is this exchange of heat energy, but it is a flow from one thing to another thing. It's not the same thing as the temperature. Okay, it's a form of energy. So first off, energy is defined as the ability to do work or produce heat. Now that to do work part of the definition is more of what you would see in physics next year. We're going to be concerned with the part about producing heat. When we're looking at our chemical reactions, heat is stored in, or energy is stored in the chemical bonds of our reactants and our products. And as those bonds are broken and reformed to form new compounds, there's an exchange of heat. And that tells us if, the reaction is going to take in heat or if it's going to give off heat in order to get the reaction to go. So first off, when we're talking about heat in chemistry class, we're going to represent that with a lowercase q. All right, so a lowercase q is going to be our heat. And like I said already, it's a form of energy. What heat does is it's going to move from an area that's warm to an area that's cold. And it's going to keep flowing until you reach what's called thermal equilibrium, where both objects are at the same temperature. So you can see in this picture down here, we have this cylinder, whatever that is, that got added to the water, and it has a low temperature of 5 degrees. And it got added into this water that had a temperature of 70 degrees. I think that says it's blocking it a little bit. So that means that the heat is going to flow into the cylinder because it's a lower temperature. And it's going to keep flowing until they're both at the same temperature. And that's going to depend on how much of each thing you have in each object's specific heat, which we'll talk about in just a second. All right, so a couple of definitions. First off, calorie, a little c lowercase calorie, okay? This is different than what you would see on your food packages. A little c lowercase calorie is defined as the amount of energy it's going to take to change the temperature of 1 gram of water 1 degree Celsius. Okay, now this is going to be very close to another definition I'm going to tell you about in a second. In fact, it's a one-word difference between this definition and something else. So the amount of energy it's going to take to change the temperature of 1 gram of water 1 degree Celsius. When you look at your food packages and everything, you're going to notice that it's a big C calorie. That's just 1,000 little c calories. It would look really bad if you pick up your bag of chips and discover it had 250,000 calories. So they put it with a big C calorie. It looks better in our food packaging. And it's just a different way of representing the amount of energy in that food. And then, I just realized I didn't clear off my drawings from the last slide. Joule, a joule is the SI base unit for heat. So SI just means the International System of Units. So that way, if we talk to somebody, in Europe or in Asia or in Africa, we all know what we're talking about because we all use that same unit and we can all understand that unit. So a joule is the SI unit. 1 little c calorie is going to be equal to 4.184 joules. That's going to be a conversion factor that we're going to have to be using later on in this unit. So 1 little c cal is equal to 4.184 joules. So let's take a look and see how these heat conversions are going to go. Anytime you do any kind of conversion, like we've done in moles and we've done in pressure during the gas laws unit, we set up our dimensional analysis. So you always start by writing your given 230 big C calories. We want to convert that energy into joules. Well, we know that this is just another way of saying it's a kilocalorie. So to go from kilo to a base unit, just calories, I know that there are 1,000 little c calories in 1 big C calorie. Sorry, that's a humongous C. You can also move your decimal point 3 spots to the right in order to convert from big C cals to little c cals. I need to get this into joules. I know that 1 little c cal is equal to 4.184 joules. Now that I have joules on the top, I can go ahead and calculate. So 230 times 1,000 times 4.184. And my sig figs, I only get 2 sig figs because of this 230. So I would record my answer as 96,000 joules. A fruit and oatmeal bar contains 142 nutritional big C calories. Remember, I just said if I want to convert from a big C cal to a little c cal, I can just move my decimal point 3 spots to the right. So that would be equal to 142,000 little c calories. That's a comma, not a decimal point. An exothermic reaction releases 86.5 kilojoules of energy. How many calories is that equal to? So I've got 86.5 kilojoules. Now I need to get that into joules first. So I know that 1 kilojoule is going to be the same as 1,000 joules. And then once I get it into joules, I can convert from joules to calories by using that new conversion factor. 4.184 joules is equal to 1 calorie. And then I can go ahead and solve. So 86.5 times 1,000 divided by 4.184. And I can have 3 sig figs. So my answer would be recorded as 20,700 calories. Okay? So what I want you to picture is a nice, warm, hot, sunny Texas summer day. You get to the beach, you kick off your flip-flops, you start running across the sand, and oh my gosh, does that sand burn? It's so hot, so you have to run right into the water to cool your feet down. Have you ever been to, one of those school football games at Turner Stadium, or maybe the soccer games at our own stadium over here? Maybe you've sat out there watching baseball or softball. What does it feel like to sit on those benches, in the middle of August or May? What about when you're watching the soccer games in January? How do those benches feel? It gets so hot in the summertime, but it's so cold in the winter. So why is it? Why do they feel so different in the hot summer months versus the cold winter months? It has to do with the object's specific heat. Okay, each object has a specific heat. Now this is the same definition as the little c calorie, except for that one word. So this is the amount of energy needed to change the temperature 1 degree Celsius for 1 gram of a substance. So this is specific to the substance that we're talking about. And you can see on the right-hand side here, there's a list of all of these specific heats for all of these different substances. When you look at this picture down here, we can see that we have a kilogram of gold and we have a kilogram of water. So we have the same mass of each of those objects. And you can see that they're both lit by the same flame, so that we're giving them the same kind of energy. But you can see that we were able to heat this gold up much, much greater than we were able to heat up this water. And that's because of their specific heats. If you look at the specific heat of gold, it's 0.126 joules per grams degrees Celsius, but water should be 4.184. But look how much bigger water's specific heat is than the gold. So that's telling me that it takes so much more energy to heat up water than it would take to heat up that gold. So let's see if we can understand some things about specific heat. So first off, which is it harder to change the temperature of, water, glass, or iron? So you're going to look at your chart over here. We're going to find water. Here's water, 4.184. We're going to find glass, 0.664. and iron, 0.45. So which is going to be harder to change the temperature of? Well, it's going to be harder to change the temperature of the water because it has such higher specific heat than the glass and the iron. Oops. Is it easier or more difficult to change the temperature of substances with higher specific heats? Well, we kind of just talked about this in the last slide. It's going to be more difficult to change the temperature of, I'm just keep making dots on here. It's going to be harder to change the temperature of objects with higher specific heats because the higher the specific heat means it takes more energy to change the temperature 1 degree Celsius. And then last question, which substance has the most difficult time holding on to heat? So what is the hardest time holding on to heat? Is it going to be something that has a high specific heat, or is it going to be something that has a low specific heat? Well, it's going to be something that has a low specific heat because that means it doesn't take much energy, again, to change the temperature 1 degree Celsius. So the things with the lowest specific heat, in this case gold and lead, means that I'm going to be able to change the temperature of that very easily. It's also going to lose heat really easily. So it's going to have a hard time holding on to that heat. All right, so as you're working throughout this unit, if you have any questions about understanding conceptually what's going on with the heat, just let me know. All right, thanks.